this lesson today, we're going to be talking about domain and range in a little bit more detail than we've talked about in the past. So just as a reminder, domain and range values, the domain value is an X value, which is also called an input value, and then the range value is a Y value, which is the output value. And if we look at this set of ordered pair that we have here, we can determine what the input and output values are, or the domain and range, just by looking at the coordinates. So we always know that a coordinate begins with an X and then ends with a Y. So all of the ones that I'm underlining here are going to be our domain values, and the ones that I'm double underlining are going to be our Y values. Now, when given a set of ordered pair, we want to list the X values for the domain and list the Y values for the range. So if we were to put this in set notation, it's just going to look like this. I'm going to go ahead and write them as 2, -4, 0, and -2. And you can absolutely put these in numerical order if you wish. And then the range values, I would just go ahead and do the same thing, -3, 6, 5, and -2. Now, when putting them on the coordinate plane, you have to be very careful of something. Since these are just a set of ordered pair, we're not going to connect the dots. Let me show you what I mean. Let's go ahead and graph this, this set of ordered pair. So I have 2, -3. I'm going to put a nice dot there. And then -4, 6, 0, 5, and -2, -2. All right. You can see that I'm not going to connect these dots at all because they're just coordinates. They're just X values and Y values, and that's all. So if you're given a set of ordered pair, this is how you're going to graph it, and this is how you're also going to put it in the proper notation. Okay, let's go a little bit deeper now. All right. This is where things start to get a little bit challenging, and you really have to put your visual cap on. So, when given a function like the one below, you must take into account all of the corresponding X and Y values. Now, I'm going to try to represent this using colors just to kind of show you how this works. But what we're going to do is determine, given this line, what are the X values? What are the domain values that correspond to this particular line? One thing to know about the line is that the line is going on and on forever in both directions, and we know that by the arrows at the ends. So, my question is this. If I were to put a dot on this line, wouldn't we say that this particular location has an X value of -3 and a Y value of 3? We know that by just finding that coordinate, right? -3 and 3. So the domain value would be -3. Okay, now let's go ahead and choose another value that's on that line. Let's go ahead and pick this one. Now, that particular location has an X value of 3 and a Y value of -1. Okay, so my domain value is 3. Now, I can go ahead and I could put a dot right here. I could put a dot right here. I could put a dot anywhere on this line. And wouldn't you agree that every single one of those dots would have a corresponding X value? Well, hopefully you said yes to that. Now, what about those arrows? The arrows mean that this line is going to continue on, right? So wouldn't a coordinate here also have an X value? And the answer is yes. I could also extend my line in this direction as well. And a point down here would also have an X value. Now you're probably thinking, well, that's a lot of X values to write. Well, there's a special way that we write the domain for a function that has infinite number of X values. And the way that we do that is like this. We usually like to do little squiggly brackets, and then we like to write X such that X exists in the real numbers, meaning that any point on this particular line is going to have a corresponding X value. Okay, now let's talk about the range. All right, let me switch my colors here. The range works the same way. Now, we could go back to that original coordinate that we looked at, and we would see that yes, it indeed does have a Y value, right? And we could use that other coordinate here, and we could say, okay, it also has a y value as well. And we could go and say that all of these coordinates also have y values because they do. So in this example, we're also going to be having y such that y exists in the real numbers. Anytime you have a straight line that has arrows at the end, it's always going to give you a domain and range where x exists in the reals. Okay, let's kind of beef it up just a little bit just to kind of get a little bit deeper with this. Okay, now let's work with some different graphs that really look different. So I'm going to go ahead and pick some nice bright colors for our graphs here. All right, let's go ahead and let's look at the domain of this first graph. So I'm looking at x values, right? So I'm looking at, this is my x-axis right here. So I'm looking at values all along that axis. Now, would you agree that this particular graph is going to end at this location here on the x-axis? See how it goes all the way down there, and -4 is the lowest x value, because that point right there has an x value or domain value of -4. The highest value is going to be here, where the highest domain value is going to be 3. And then the domain values are going to be everywhere in between. You can see that this coordinate right here will have a domain value, and its domain value will be -2. I could say this value right here is going to have a domain value of 0, just by making my coordinate my x and my y. Therefore, the domain of this right here is going to be x such that I want to say between. So therefore, I'm going to say -4, that's my lowest, is less than or equal to every domain value, which is less than or equal to 3. This is just a fancy way of saying that every single point in between -4 and 3, and including that -4 and 3, are going to be located within the domain. Okay, again, like I said, this is a very visual concept here. So let me go ahead and change my pen color. Let's talk about the range. Now the range is going to be my y value. So my highest y value on my y-axis, in our case, is going to be 2, right? It's going to end, this is it, right there. And my lowest is going to be at -2. And it's also going to include every point in between. So this point right here will have a corresponding y value. We'll have a corresponding y value. But what if I put a point up here? It doesn't have a y value because it's not on the graph. So therefore, y such that my lowest is -2. You always want to put the negative number down below. Is less than or equal to y, which is less than or equal to 2. So it's saying that all the numbers between -2 and 2 are possible range values for this function. Because let's just check one. Isn't 0 between -2 and 2? So wouldn't I say that right here, this coordinate right here has a y value of 0? Isn't it 3, 0? So my y value is 0. It's also on the other side, -4 and 0. So that's going to be one of my y values. Okay, let's look at another one. Take a look at my domain. Okay, I'm looking at my lowest x and my highest x. So my lowest x value is going to be right here. I'm drawing a vertical line because, that's where you're going to be able to see your domain values right there. And then my x, my highest, I keep erasing it, I'm sorry. My highest x values are going to be there. Notice how the points that are represented on this graph are filled in dots. Filled in means that it includes that point. So I want to represent my domain by saying x such that my lowest domain value of -5 is less than or equal to, which means it includes that point, x, which is less than or equal to my highest domain value, which is 4. Now looking at my y, let's look at my highest and lowest y values. This coordinate right here, notice that it has no arrows at the end, so that is my highest y value. And then my lowest y value is down here. So therefore, y such that my lowest y value is negative 3, which is less than or equal to y, which is less than or equal to positive 4. And there we have it, my highest and lowest. So that is my domain and my range of the given graphs. Okay, let's try a couple more. It's a tricky concept. Okay, now I'm back and I have an absolute value function. So you can see with the absolute value, I am given little arrows at the end, which means that this graph extends in the positive direction. So let's talk about domain values. If these are going to continue on and on, right, do I have a high and low domain value? Well, each of these coordinates are going to have an x value, right? Aren't they going to have an x value on and on and on and on forever? Yeah, in both directions. So therefore, the domain of an absolute value graph that looks like this is going to be x such that x exists in the real numbers. They're going to be infinite. But when we're talking about the range, it's going to be a little bit different in our case here. Take a look at this. Now, like we said, those graphs are going to continue on, right? Which means that for every point, you are going to have an x and a y coordinate, right? I could even be way up here on my graph, but it's still going to have an x and a y. But what about right here? Is there an x and a y right there? No. This right here is the lowest point where there is an x and a y value. What I mean by low is that your y-axis extends up and down. Therefore, this coordinate right here is the last coordinate, 0, 0. So that means y as 0 is the last coordinate. So how we represent that is we say y such that y is going to be greater than or equal to 0. And you're done. The next example is unique because it has an open dot and a closed dot. And the open dot that you see up here means that it excludes the point. So it does not actually include that point. And then unlike this one over here, this one includes the point. Kind of like inequalities, same idea. So let's look at our domain values. Okay, the last point that will have a domain value, let's go ahead and look at this. It's going to be at this point, but it's not going to include it. The highest is going to be right here, and it is going to include it. So the way that we represent that is we say x such that, now my lowest number is -5, but this time it does not include it, which means I'm going to use the symbol less than. X, which is less than or equal to, because it includes that higher number, which is 0. And we're done. Now, looking at my range, hopefully my colors aren't getting too confusing here, but my highest range value is at that non-included +5, and I'm getting that number right on my axis. And then my lowest is going to be at that -4. So, and everywhere in between. So to represent that, I'm going to say y such that my lowest number, which is included, y, which is not included, 5. Unfortunately, there's no canned answer for these types of problems. You truly have to be thinking about the graph and all of the little bits and pieces that go along with it. Okay, now what if we just are given a picture of a graph? For example, I am telling you here that this particular picture is of the function y equals x minus 3. And if we were to graph it on the graphing calculator, we would get the picture that you see here. And we want to know, well, what's the domain and range? Well, remember, in the graphing calculator, it's never going to tell you that these two lines extend forever. So I'm going to go ahead and do that for you by showing you my little arrows. Way back in the first example, we talked about anytime you have a linear function like this, your domain and range is always going to be the same. There will always be an x value for every y value. And so therefore, we're going to represent it x such that x exists in the reals, and y such that y exists in the reals. Same idea. But let's say it's not as easy. Let's say that I don't give you the picture. How could you figure it out? It says determine the domain and range of the functions below. Also notice that I put those two functions in function notation. Just remember that f of x is just another way of saying y. So what we could do is use our graphing calculator. Go to your y equals and substitute your function into your y sub 1. I'm going to go to y equals and then negative 2x minus 5. And you know what I'm going to do? I'm going to graph it. You can see that I'm given another line. It's a linear equation, and therefore my domain is going to be x such that x exists in the real number system. And my range, or my y, is going to be y such that y exists in the real numbers as well. Don't overcomplicate it. If you're given a line, your domain and range will always be the same. But what if it's not a line? Look at this next example. We know that that function notation is just another way to say y. So let's go ahead and put this into our graphing calculator. It's a little bit more complicated. I'm going to go to y equals. I'm going to clear everything out. And I'm going to put x squared plus 4x plus 4. And I'm going to graph it. And you can see that I'm given a nice parabola. And it's an upward-facing parabola. And you can see that it's very similar to the absolute value example that we did. And what I mean by that is you can see that my domain values are going to go on forever, meaning there's always going to be a domain value, which means x such that x exists in the real number system. Now for my range values is a little bit different because I have a low point. Do you notice that my low point in my range is going to be at the x-axis? That would be the lowest range value would be 0. So I'm going to say that y such that y is greater than or equal to 0, because it's going to be every number that's greater than or equal to that 0. So you can always just take a function alone and put it in the graphing calculator and actually look at the picture. It's really just like what we've been doing throughout this section, looking at a picture. Okay, that brings us to the end of our domain and range section.